Hi, my name is Lorenzo Lamberti, and today I'm going to present our work entitled Low Power License Plate Detection and Recognition on a RISC-V multi-core MCU-based vision system. But let's first introduce the problem. Automatic license plate recognition consists of predicting all the license plate numbers in an image. This can be seen as a specific case of optical character recognition, and usually we split it into two phases. First, we detect the license plate, then we transcribe its content. In the last years, deep learning made OCR easier when compared to traditional computer vision approaches. But ALPR still has a very high computational complexity, and therefore it has been implemented on high-end devices only. For example, it has been implemented on HPC servers, on powerful GPUs, on FPGAs, and even on mobile devices. But still, there are no evidences of ALPR on IoT devices. If we want to bring ALPR on the IoT world, then MCUs are the ideal platform for several reasons. First, they are low power and IoT devices are usually battery operated. Second, they are low cost. And third, they are highly flexible because they can be programmed. But on the other hand, MCUs present severe limitations. The memory is very limited, up to few megabytes, and the computational power is constrained too, because we usually talk about one single core running up to a few hundred megahertz. So we experience a very low Mach throughput in the end. And the focus of this paper is to overcome all these challenges and demonstrate for the first time that low power MCUs can perform multiple DL tasks at approximately 1 FPS within a very low power envelope of 100 milliwatts. But first, let's see why ALPR is such an intensive computational task. We will be analyzing 4 works that implemented an ALPR system in the literature. The first one addressed just part of the problem, so just text recognition, and they did it with a BLSTM. The computational complexity for this algorithm is enormous, around 360 gig operations, and therefore they used a very powerful FPGA by Xilinx, which was having a power envelope of over 9.5 watts. The second work address the simpler part of the ALPR pipeline, so object detection, and even though the complexity is much lower, the power consumption is still very high because they use the same FPGA, so about 7 watts. And the third work is actually the only one that is implementing the full ALPR pipeline, so detection plus recognition, and they did it with a Raspberry Pi 3 coupled with a camera. But still, even in this system, the power consumption is way over 3 watts of power consumption. The last work, again, just addressed the object detection part of the problem, and they did it with an Intel neural accelerator. And even in this case, we can see that the power consumption is still around 2 watts, so still too high. Now we're gonna see 3 devices that could implement an LPR system, but they haven't been used yet by the literature. But all 3 of them still feature a too much high power consumption. We have the Google Coral with 2 watts and both Pixie 2 and ASCII Lens with about 700 milliwatts. Lastly, there are a couple of devices that could fit into the targeted 100 milliwatt of power envelope, but the ARM Cortex M3 actually has been shown to be not capable of performing real-time deep learning vision tasks, while the last work, as we will see very soon, actually targeted a problem that was much simpler in complexity with just 41 million of Mach operations. So our contribution is that we present an hardware-software co-design flow that allows to gain an energy-efficient sensing platform. We first determine the hardware and software building blocks. For the software part, we split the ALPR pipeline into two simpler tasks, detection and recognition. And for the hardware, we choose to use GAP8 coupled to an HIMAX low power camera. Then we go through an optimization process based on the specifics of the hardware characteristics, and we applied some compression techniques such as quantization. And lastly, we prove the accuracy of the whole system on both public datasets and with an in-field testing. And we also prove the energy efficient of our system, achieving 73 times less power consumption on ALPR when compared to the state of the art. So let's take a look at the hardware and software components. For the software part, we split the ALPR pipeline into two stages. The first one is the detection one, and we used a single-shot object detector SSD. This is a fully convolutional neural network that takes in raw images and produces bounding boxes for each license plate in the image. Then we crop and resize each license plate, and we fed it to the second stage, the recognition one. We used a network called ALPRNet, which is a fully convolutional segmentation-free deep learning approach. This is composed of a first CNN as a feature extractor that outputs a two-dimensional tensor, and this tensor is then fed to a decoder that predicts the characters. Both these topologies are very compact. In fact, they are under 5 million of parameters and under 1 gigamach operation for each inference. Talking about the hardware, we choose to use GAP8 by Greenways Technologies. This is based on the POP architecture. It features one main core, the Fabric controller, and a cluster of 8 parallel cores. It has 3 levels of memories from L1 to L3, and it can achieve a throughput up to 1 gigamach operation for each second. We couple it with an ultra-low power camera by HIMAX that has just 2 milliwatts of power consumption, and we used some software deployment tools by Greenways Technologies, the so-called GapFlow, which includes the NN tool for quantization and the autotiler for the deployment. And we choose to use GAP8 because single-core MCUs have a very low throughput. For example, if we try to run a classic object detector as YOLO on an ARM Cortex M7, this is estimated to take between 23 and 15 seconds to be processed, which is too much for a real-time inference. So let's now talk about optimization. The optimization of the first stage goes through 3 phases. First, we choose the network topology. We experienced that MobileNet V2 is much better than MobileNet V1. It has a better accuracy, less size, and much less MAC operations. And then we replaced the SSD heads with the SSD Lite counterpart, which uses depth-wise separable convolutional blocks. This saves another 1.5 million of parameters and reduces by 30 million the MAC operations. Then we tried to choose the input size of the images, and we saw that increasing the input image size slightly increases the accuracy, but on the other hand, the MAC operations increase quadratically. So we choose to prioritize the MAC operations, and we stick with the QVGA format, which is also the format of our camera. Then we performed 8-bit quantization, and we also applied quantization-aware training to mitigate the accuracy degradation. And with this, we just lose about 0.9% in accuracy, while reducing the model size by 4 times. So from 12 megabytes to just 3 megabytes. Now we move to the second stage of the ALPR pipeline, the recognition stage. And first, we removed the layers unsupported by the gap flow because ALPRnet was having a layer that was replicating a tensor, and this was not supported. We replaced it with a fully connected layer with the same output size. And by doing so, the accuracy doesn't change a bit, while the number of parameters increases by 0.7 million. So for reducing the size of the network that we just increased, we halved the size of all the fully connected layers in the residual block, and by doing so we decreased the number of parameters by 1.4 million, and the accuracy didn't drop even in this case. Lastly, we applied 8-bit quantization just as before, and we experienced no accuracy degradation at all thanks to quantization-aware training, and we reduced the model size by 4 times, so from 4 megabyte to just 1 megabyte. So in the end, the complete pipeline optimized has a total size of 4.1 megabytes, and a single inference takes just 687 million of MAC operations, and these when deployed on GAP8 has a processing time of just 0.92 seconds, which translates in a throughput of 1.09 FPS. Let's move now to the experimental results. We collected and labeled 63 images, 15 with Italian license plates and 48 with Chinese ones. We acquired the images at 5 distances from 0.3 up to 4 meters, and by doing so we introduce variability in the size of license plates and characters. So we evaluated the complete ALPR pipeline, investigating the maximum detecting range, and the pipeline works in the full 0 to 4 meter range, detecting 98% of the license plate correctly. So the minimum size of the plates that we are able to detect is 30 by 5 pixels. Then we investigated the maximum recognition range. In this case, the pipeline works in the 0 to 1 meter range with 100% of characters recognized correctly, and the minimum size of the characters that we are able to recognize is 8 by 16 pixels. We also evaluated the whole system power consumption. The system on a chip takes 108 milliwatts, the camera just 2 milliwatts, and the L3 memory another 8 milliwatts. The power adds up to a total of just 117 milliwatts for the whole system, and a single inference takes 108 millijoule to be processed. This makes our solution 73 times less energy demanding when compared to the best ALPR system in the literature, which needs about 3.12 watts of power envelope. So in conclusion, we present the first low-power edge device for automatic license plate recognition, and on real-world data, the pipeline recognizes numbers when the size of the plate is as small as 30 by 5 pixels. And thanks to the optimization strategies, the inference achieves a throughput of 1.09 FPS with just a power cost of 117 milliwatts. And our solution is the first MCU device embedding such a level of complexity, resulting to be 73 times more energy efficient when compared to the best ALPR system in the literature. So as a final remark, we would like to point out that our approach is completely flexible and it can be used to deploy similar visual deep learning tasks on edge devices. And to foster future development, we open source the models and the firmware at the GitHub link below. So my presentation is now over, and I really thank you for your attention.